So in section 1.2, we're looking at GCF, greatest common factor, and difference of squares. Difference of squares is going to kind of be our preview into factoring. We're really going to go into the factoring next week, factoring quadratics, factoring polynomials, but kind of a preview, kind of a hint, a special case as we get to that. Now, we talk about GCF. We can remember factoring, and you have distributive property. Now, those two things, factoring and distributive property, are opposites of each other. So if you took an expression, you factored it, then you did distributive property to it, you're back to where you started. Kind of like when you had a square root and we squared it, got you back to the original. It's the same idea here. So distributive property, you multiply out the term, which you did a little bit of in that last section. Factoring, you're taking out a common factor. We always want the greatest common factor, so we want to simplify it down the best way we can. Thinking of coefficients, like common terms, and then exponents also, when we look at that. So, whenever we have to find the greatest common factor, we just undo the distributive property. So let's think we go x squared minus 5x. What would that have started as a distributive property problem? Like that? Okay, both terms have an x in them. I can factor it out, put it on the outside. I'm left with x minus 5. You take the quick second look, make sure you got everything. X minus 5 is nothing. No common factors left there. Simplified. Okay. On last class, you could have gotten that problem, x times x minus 5. I said multiply it out. It's just the reverse of it. You're going to see out throughout this unit, whenever we multiply, whenever we factor, we're really just looking at either side of the problem. We're going to have to learn how to put it together, but the nice thing is there's shortcuts, and there's patterns we pick up, starting with today, that makes things easier for us. So let's go to 9x cubed plus 36x squared. Okay? Give me a coefficient term I can factor out. Common factor. 3 would work. Give me a bigger one.
9.
Yeah, you want to do 9. You want to always take the bigger one. If you took 3 out, you're left with 3 times 12. On the inside, that still has a common factor, so make sure you factor it completely. So 9 comes out. Now, what is the largest, try again, what is the smallest exponent they have in common? Largest to smallest exponent. I have x cubed, I have x squared. Okay, how many can I take out?
2.
Yeah, I can take out 2. I didn't say that right, but I think you got what I meant. Okay, I can take out an x squared. It's not more than the smallest exponent. Sounded better. All right, so I take out 9x squared from 9x cubed. What's left there? Good. Take that out from 36x squared. What's left?
4.
It's a 4, yeah. Now, the other thing to be aware of is if you factor out all of a term, like if this was to the 4th here, and I factored out the whole thing of 9x cubed, you would just leave it as a 1 when everything's factored out. It's not 0 when you factor out. There's just a 1 left over. All right, let's build it up a little bit more. Let's go something like 28x to the 4th, y to the 3rd, plus 35xy to the 3rd, minus 14x squared, y squared. Okay, we work on it through steps. We first look at our coefficients, the numbers out in front. We look for some property they have in common. If you can see the quick common factors, makes it easier. What do you see?
7.
Yeah, 7 comes out. Even if it was one like maybe this 35 is another factor of like 84, and you at least try 7 and you can keep going, That's fine. Just try to factor one out. If you don't get it all in one step, you go back, get the rest. But 7 comes out. Okay? How many x's can come out? I got 4, 1, and 2. So just 1. You can't take more than a term has. It's not the greatest, it's not 4, but it's the one that at least all of them have. And then y's, how many? Okay. So now I got 4 and what in this first term? What's left? And? Okay. Second one? 5 comes out.
It's x cubed. 4. It's 4x cubed.
There you go. 4x cubed y. Let me move that over. All right, we got 5. X comes out. I had x or y squared comes out. So it looks like just a y left over. How about here? Definitely the negative. Don't forget the negative when you're factoring. Same idea with distributive property. Don't forget those negatives. So we said negative 2. Yep, and just an x. Everything else is accounted for. We're here. Now, the greatest common factor, in the big picture of what we're doing in this unit, it's a little step at the beginning of the process that really just makes things easier for us. We're going to get to the point where we're going to have to factor something like 4x cubed y plus 5y minus 2x. I'm going to factor that down. So anytime you can take numbers out, it gets it smaller. Just like we did in the last unit where we had simplifying the radicals, or anytime you reduce a fraction. Okay? By factoring that out, it makes this last leftover piece easier to deal with. So it's a little step in the bigger process we're working with, but just making sure we know that it really just is the opposite of distributive property. So now, let's look at difference of squares. So we're going to start with just a general form of what we're doing here. Difference of squares means x squared minus y squared. Not actual squares, the shapes, but squares as the number. It's a difference because it's subtraction. We will not have the addition of squares or the sum of squares. It has to be subtraction. So as you look through these today, there will all be subtraction. One term minus the other. When we bring in all of our factoring, and this is kind of a quick way through it, it has to be the subtraction. So the difference of squares tells us that we can write this as 2 terms, x minus y, x plus y. So it goes from being 2 terms squared to 2 binomials. Now what you would have saw yesterday when you multiplied, and we just factoring in and multiplying, opposite process. So I'm going to take this and multiply them. And I did x minus y, x plus y. I would have x squared, negative xy, xy, negative y squared. My like terms in that diagonal became 0 because it's xy minus xy. That was nice. There was nothing left over. So my result is x squared minus y squared. So it simplifies nicely. So we see something that's 2 terms squared and subtraction. We clearly know it's going to factor down to that. Didn't have a middle term, which is good. But what we've also shown here is since we did it with x and y and it worked, it's going to work anytime we have squares involved. So we don't even have to go back and check with the multiplying. So what if I did something like x squared minus 1? Is this a square? Is that a square?
Yes.
It could be. Do we want it to be? You want it to be. It makes it easier. Okay, 1's a square. Look. X squared minus 1 is x minus 1, x plus 1. it's not that we have two x minus y's. One term is going to be subtraction, one's going to be addition. And the reason is it gets these to be opposite. So I have x squared, or x squared plus x squared minus 1, make one subtraction, one addition. If I did it with both negative, the problem would be it comes out to be x squared minus 2x plus 1, and it doesn't simplify back to it. Which we'll deal with these next week, where we multiply out and they don't end up being two terms, and that's something we get to, but for today, it's a special case that if we pick up that pattern now, it makes our process easier. Okay, well let's add a little more to it. Let's go now x squared minus 49. What's that going to be?
X minus 7x plus 7.
Okay, x minus 7x plus 7. What if we did 49x squared minus 1? Okay, so this is a square, right? You're saying it's 7x if we took the square root of it? Yeah, it's going to be 7x minus 1, 7x plus 1. It doesn't matter if you write the addition or the subtraction first. As long as you have both of them, we have it covered. Now, that is it in its basic form. Let's add the more to it and kind of start unwrapping the different ways we can get to it. So I'm trying to program you now to look for perfect squares so you then can simplify it and write the factor form. Then you look at that problem. What's the issue? Not perfect squares, right? Okay. What's our next option then? Ah, do they have something in common? Okay, 3 comes out. I'm left with x squared. I got that part. You can get the next one. It's 48 divided by 3. 16. Is that better news? Oh, look, perfect square. Perfect. Square. Perfect square. Factors to be x, what? Yep, minus 4x plus 4. So we can even start to hide these perfect squares within different expressions where we have to factor something out before that. Okay, how about this? 49 x cubed y minus 25xy cubed. Do we have perfect squares there? 49, 25, we're good with, right? Okay, what's the problem with x's and y's? I got a cube, then I have just an x and a y by themselves. But is there a perfect square, a difference of squares hidden there? What can we factor out of both? What is in common between both of them? How many x's does each term have? They each have at least one, right? How many y's does each term have? Okay, so let's take those out. Okay? Clear those out of the way. See if we simplify it down. It's just like we're reducing a fraction. We just want to get it to smaller terms. So I got now 49 x squared minus 25 y squared. Now is that looking better for us? I think that is better. Now we have in the first term like a 7x squared. In the second term, it's a 5y, and that's all squared. So we can factor now, get xy, then it's going to be 7x minus 5y, 7x plus 5y. So we have the basic we looked at here. Factors, breaks it down. We can only do so many of these. Then we start kind of throwing in, looking for common factors. So as you look through and do the practice problems, when these come up, and you immediately look at the problem and go, there's no perfect squares here, we look to factor. Or you immediately look at it and go, I don't have an x squared, y squared, you look to factor. By factoring them down, it's going to get down to those nice perfect squares. You simplify, we're there. Anything that's not working out, we cover that next week as we go into more of the factoring, especially if it's like 3 terms. For right now, that's what we look for. So with that said, what if we did x to the 4th minus 16? What's the square root of the first term? Okay, square root of the second term. It's 4, right? So, following the rule we have, even though that is an x to the 4th, which is really x squared squared, I'm going to make it now x squared minus 4, x squared plus 4. Is that following the rule? Okay. Can we keep going? Okay. Can I factor both of those terms down? Try again. Can I factor both of these terms down? Oh, why is that random hand circling the thing? What's wrong with this one and why I can't factor it? Ah, it's not subtraction. This one fits. This one's still a difference of 2 squares. This one is not. We find out later what this actually factors to be. It's not a real solution. It doesn't work for us. Doesn't mean we can't use this. It just means we can't break it down further. What we can do, though, is use this one. So now I'm going to break apart that one. And go x squared minus 2. Not x squared. X minus 2. And x plus 2. Bring along the last term. Still there. Still fine. Still works. We just can't simplify it. So we looked at something that had higher than an x squared. We factored. We could factor again, but you can only factor the thing that's a negative, that has the subtraction in it. Okay? So you're going to try now x to the 8th minus 1. All right, hopefully we see the first one is x to the 4th minus 1, x to the 4th plus 1. First step there. Okay, can we keep going? Can, with both terms or just one? Just one. Which one's kind of the tag along the rest of the way? Which one's finished factoring? Yeah, the addition. Do not factor this down. It's not a real solution. If it's not a real solution, it's an imaginary solution. We actually have imaginary numbers because they're not real. We really do. Well, we imagine we do because they're imaginary. That's later. That's end of the year. All right. So, x to the 4th minus 1 becomes what? Good. Plus 1. Good. And then our tag along. Are we finished? No, we keep going. First term, right? Factors more? X minus 1, x plus 1, x squared plus 1, x to the fourth plus 1. We look now, there's nothing left that is squares and subtraction. Finished. It's factored down. Who would have guessed that x to the 8th minus 1, something that looks so simple, could factor down to be 4 terms? 2 with just x's, 1 with an x squared, and 1 with an x fourth. But that is the beauty of difference of squares. So, back to this main idea. This is a quick way we're going to be able to factor with difference of squares. You have squares, it becomes just the terms, addition and subtraction for each one. We can arrange them different ways. We can hide common factors in them. We can change it so you factor and factor again, but it's working through that process, paying attention that it's subtraction in squares, not using addition. So, your assignment for this